So welcome back. This is our lecture number 15, and now we're going to talk about learning Bayesian network parameters from data using the maximum likelihood approach. So we have already discussed this idea of learning parameters from data. The first time that we discussed this, it was when we were looking at the Bayesian networks as classifiers. We also worked with this idea in one of the tutorials, and you also worked with this in the first assignment. So I think that now you're already very used to this idea of learning the parameters using complete data. And actually the approach is very simple. We just count the frequencies that we are interested in, and this is going to be our estimates. So this is the simplest scenario when we don't have a missing data. So we call this the complete data scenario. Now we're going to extend this, and I'm going to show you that when we count those frequencies in the complete case scenario, that corresponds to a maximum likelihood estimate. So it's going to be interesting to know that what we are doing corresponds to a principle that is frequently used in machine learning to learn the classifiers, that it is idea of maximum likelihood. So we're going to define what is maximum likelihood. You're going to see that there's a very simple idea behind it, and we're going to show that the parameters that we estimate with the frequencies corresponds to this maximum likelihood estimate. We're going to extend this idea once more, and I'm going to show you how we can learn from incomplete data. So in this case, we have some missing values in the data, and we want to learn the parameters. You're going to see that's going to be a slightly more complicated scenario, and you're going to need an algorithm that we call the expectation maximization in order to solve this problem. You're going to see that the idea behind expectation maximization is very simple, and we're going to see how it works and one algorithm for learning the parameters for incomplete data. This lecture will be complemented by the next lecture when we're going to discuss how we learn the structure of the Bayesian network from data. So in this case, we're going to learn the graph. And if we use these two approaches, we can learn the entire Bayesian network from data. We can start learning the structure, and later on we learn the parameters according to this structure, and we have learned the entire Bayesian network from data. That is one approach that we call the machine learning approach for learning Bayesian networks, because we're going to rely only on data to come out with the structure and the parameters at the same time. So let's get started and see how we can learn from the parameters from data using the maximum likelihood approach. So this is one example of a Bayesian network. If you haven't seen this before, it's related to medical diagnosis. So we have here on the top different diseases, and in the bottom we have different symptoms. And we want to give a set of symptoms. We want to know which is the most likely of those diseases. So we also have here a data set for this Bayesian network, and in this case this data set is called incomplete. It's incomplete because we have some missing values, like here and here, and we denote those missing values by this interrogation mark. So we have here and so on. And we have already discussed it very briefly this before, but in the case that we have missing values and we are doing inference instead of learning, so we are interested in inference, that would not be a big problem for the Bayesian network, because we can deal with those missing values as being like hidden variables where we do not give values to them when we make a query. So basically, in the process of inference, what's going to happen is that those missing values will be summed out in the inference process, and we can still compute the probabilities ignoring those variables. So this idea can be useful, for instance, in the case that we are doing classification and the test case having missing values. So we can still do the classification actually very easily using the Bayesian network by giving one example with missing values. We consider that as non-observed variables. We sum out those variables and we consider the remaining ones in the inference process, and we come out with one classification. So this property of the Bayesian networks of easily dealing with missing values are going to be very important in this lecture. We're going to use these in order to learn the parameters from data. So we're going to see later on that learning parameters in the presence of missing values with incomplete data will require a little bit of inference over the Bayesian network. And we're going to see that in the future slides. So I'm going to start now with the complete scenario case. It's going to be a much easier case, and we move on to the incomplete scenario in the second part of this lecture. Okay, so in this lecture, we're going to assume that the structure of the Bayesian network is given to us, and we're going to concentrate in learning the parameters. And we may ask where this structure came from, and there are three main sources of information where we can extract the network structure. One is from data, and we're going to see that in the next lecture. And the other two we have already discussed a little bit. One is from what we call the design information. So imagine that we have a problem that is like dealing with images. So the image has a structure of a grid, and we can use that structure to model our network. So the structure of the network came from the specification of the problem. Another example is a hidden Markov model that has a fixed structure. So when we are dealing with problems that can be solved by hidden Markov models, we already have a predefined structure that I'm going to use in order to solve the problem. So another source of information that we can use to build the structure of the Bayesian network is working with a domain expert. In this case, we can ask questions about what are the reasonable independence assumptions that we can make for this domain, and based on those assumptions, we can start building the Bayesian network structure. So in this figure here, we illustrate these two approaches. One is what we call elicitation. That is the process of asking questions to a domain expert in order to figure out what's going to be the structure or the parameters of a Bayesian network. And the other process is what we call learning, where we obtain that information directly from data. And we can compose these two approaches, right? So we can, for instance, learn the structure of the Bayesian network using elicitation, so asking the person, and we complete that structure with the parameters that we learned from data. Or we can use the pure approach. We can use elicitation in order to come out with the structure and the parameters, or use learning to come out with the structure and the parameters as well. So in the case that we are using learning, the approach is that we have what we call a true distribution, this P star, that we don't know it, but we want to model that distribution using the Bayesian network. What we have is a sample, right? So a set of examples, cases, instance. We have several different names for that, and that compose a data set D. This data set, we call that it is IID, right? It means that it is the sample is independent and identically distributed. So by independent, we mean that one instance the observation of one instance will not change the probability of observing another instance. So they are independent of each other. And identically distributed, it means that all those instances came from the same distribution, that is the distribution P star. So in the next slides, we're going to see a few cases that are very common when we want to learn the Bayesian network. So there are the possibilities of working with structure and parameters. Let's take a look on them. So this is the easiest case, and the first one that I'm going to study in this lecture. It is called the no structure and complete data. So what we have is a given Bayesian network structure that we obtained somehow, and represented here by this little Bayesian network here. And this Bayesian network, it factorizes the true probability distribution P star. Or at least it's a good approximation for that. So we have some reasonable independence assumptions that may be not completely true in the P star, but they are at least a good approximation for P star. And we also have a data set that's represented here with complete cases. So we have instances right, with the values for all the variables that we have here. So there's all instantiations, and those instantiations mention all the variables, so it's a complete data. And we're going to go through a process that we're calling here the inducer, that can be a very simple algorithm. In the case of the non-structured completed data, is just estimating the frequencies that are parameters for the model, and we come out with these conditional probability tables that are going to complete with the structure in order to get the Bayesian network. So the second case, we have the no structure and incomplete data. So in this case, again, we have a given structure, and that we hope that is a good approximation for the true probability distribution P star. And we also have an IID sample of P star, but now with some unknown values. So we have here some unknown values. So basically, those values were not recorded in the process that gathered the data, and we have to deal with them. So now the problem is going to be a little bit more complicated, and we cannot just estimate the frequencies using the approach that we used before, but we see that we can deal with missing data using an algorithm that we call expectation maximization. And I'm going to say that this algorithm is actually very simple, the idea behind it, and we can easily implement that in our Bayesian networks. So we're going to give here those two pieces of information, the structure and the data set to the inducer. And this inducer now is going to be a little bit more complicated, not just in counting frequencies, but also in doing a little bit of inference. And then we come out with the conditional probability tables that are going to complete the structure, and we're going to have a complete Bayesian network. So a third case is where we have what we call latent variables. And the latent variable is a variable that is never recorded in the training data. So for instance, we may have a variable like this variable age here, and when you look at the data set, we never record a single value for this variable. You're going to see that this problem is a little bit more complicated, but still solvable by the same expectation maximization algorithm that we mentioned in the previous slide. And one example where we have latent or hidden variables is in the case of the hidden Markov model. So this name hidden Markov model, the hidden comes from these hidden or latent variables. So we have in the hidden Markov model, we have these two sequences of variables. Here on the top, we have what we call the hidden or latent variables. Those variables, we may not observe them. What we're going to observe is actually those variables here at the bottom that are the emissions, right? So these are the emissions. So in this case, we could be, for instance, be interested in learning the parameters of the hidden Markov model. So remember that the hidden Markov model, they have two sets of parameters. They have the emission probabilities and the transition probabilities, as well as the initial state here, right? So the probability of the initial state. And so we'll be interested in learning these three pieces of information based on only in the information of the emission. So it's going to be like a sequence, like you have an umbrella or not have an umbrella, observing an umbrella, not observing an umbrella, and we want to learn all the parameters. So it's going to be a slightly more difficult problem because we're going to have a missing information about all these states here. So in this task, we are interested in learning the structure of the Bayesian network. So we're not going to cover this in this lecture. We're going to postpone it to the next lecture to cover this topic, but we can imagine how it's going to be. So we start with a set of random variables and a data set, and we're going to give these two pieces of information to our inducer that come out with the structure as well as the parameter. So in this case, it's very clear that the learning of the structure and the learning of the parameters is really tied together in a way that is difficult to come out with a structure without the parameters, right? So it's a kind of obvious observation, but when we have a certain structure, this structure will provide us a certain factorization, and the parameters that are different CPTs will depend on the factorization. But also because the process of selecting one structure will involve the assessment of the structures that we have, the candidate ones, in order to see which is the best one. And in order to assess different structures, we will have to compute the parameters for that structure in order to see how good are the structures. So we can use a principle like a maximum likelihood, but in order to estimate the likelihood of each structure, we need to compute the parameters. So in this case, it's going to be difficult to separate the learning of the parameters from the learning of the structure. So you're going to have this as a single output of the algorithms. And this is the last scenario when we have unknown structure and incomplete data. So it is the most challenging of all the scenarios because we have just the random variables, the data set with missing values. Sometimes we may even have latent variables that make the things even worse, and we do give that information to the inducer, and we have to come out with the structure as well as the CPTs. Okay, so let's get started discussing how we can learn the parameters from complete data. And let's use a very simple example. So we have a small Bayesian network here on the right where we have 3 nodes. One is health aware, age, another one is smokes, and the other one is exercise. And we can expect that there is a causation. If a person is health aware, it's very unlikely that person smokes. It's also very likely that that person exercises. So this is the general idea of this example. And we're gonna also assume that we have a data set. In this case, the data set is this guy here. I'm gonna make it slightly different from the probability distributions like this one here by using this border. So it's going to represent, so you can distinguish the data sets from the probability distributions by the border that you're going to put around the data sets. So the data set is a set of cases, and now we assume that all cases have all variables observed. So it's a complete data set. But there is also these 2 assumptions here that we have discussed before. The cases are generated independently and according to their true probabilities. So it comes from the same true probability distribution. That is what we call the IID assumption. IID assumption, right? And if we have this IID assumption, what we can do is to transform the data set into a probability distribution that we call the empirical distribution. And we're going to represent this by P and with this letter D here. And this empirical distribution is basically a full joint distribution for all the variables. So we have here the 3 variables that we have in the data set, and we're going to estimate the probability by counting the number of examples that we see in the data set. For instance, we have this instantiation here, age SE, all true. We're going to find it here, age SE, and also here, age SE. So we have 2 instantiations, 2 examples over a total of 16, so the probability is going to be 2 over 16. And we can do this for all possible combinations of the variables age, S, and E, and because they are binary, we're going to have 8 possible combinations here. So in practice, we don't compute this empirical distribution because this table is going to be huge. Here, because we are only working with binary variables and a small number of variables, it is very small, but it will grow exponentially with the number of variables. So what we do is when we compute the parameters, we don't go through this process of building this empirical distribution. We go directly from the training set to the parameters. But this idea of the empirical distribution is actually very useful too in order to understand what is the process that is happening when we estimate the parameters. So we can think that we are going from data to the empirical distribution, and from the empirical distribution to the parameters. It's going to be one extra step, but it's going to help us to understand how it works. But in practice, we jump this middle step and we go directly from the data to the parameters. So the empirical distribution can be a little bit more formally understood in this way here, as expressed by this small equation, where we have the probability of a certain assignment age, S, and E by being the ratio between the number of cases that we saw in the data set that match this assignment by the total number of cases that we have in the data set. So for our example that we have here, we can see that, for instance, this entry here corresponds to a person that is health aware, smokes, and exercises. So we have two different cases that gave origin to this probability here, 2/16. This one here, we didn't see it in the training set, corresponds to a person that is health aware, smokes, and don't exercise. So we are saying that because we have a limited number of cases, that the probability is going to be 0. But that is very dangerous because we have just a small number of cases. So probably it's going to be very difficult to find the person with that profile, but certainly it's not impossible. We should only assign 0 probabilities when we are completely sure that case, that instantiation is impossible. Otherwise, when we do inference in this Bayesian network and we have a 0 probability, this 0 probability is going to multiply by the other probabilities and it's going to be 0. So that's going to be very dangerous and it can lead to overfitting. But we haven't seen how to deal with this case before when we discuss a classification. One technique that we can use is the Laplace smoothing, where we change this probability from 0 to a number that is close to 0 but is not 0 anymore, and it's gonna help us avoiding the overfitting. We have another case here that seems to be very common. It is a person that is health aware, is not a smoker, and exercise. So I'm going to see 9 cases of this instantiation here. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. All right, it seems correct. Okay, and once we have the empirical distribution, we can start estimating the parameters. So for instance, this parameter here, that is theta s given age, it is the probability according to the data that we have. So it's going to be our empirical distribution for this data set of a person being a smoker, given that that same person is health aware. Right? And in this case, what we can do to estimate this probability here is to use the Bayes conditioning. So we know that this conditional probability here is going to be the ratio between the probability of being health aware and a smoker at the same time divided by the probability of being health aware. So we saw this. This is basically the definition of the conditional distribution, and we can start computing this. So we can look our empirical distribution. We can eliminate the variables that we are not interested by summing out the variables, and we come out with these numbers. So we have here 2 entries that match health aware and smoker, and we can sum these 2 entries here to eliminate the variable e. So in this case, this 2/16 that we have here is the sum of 2/16 plus 0/16. And for this guy here, the probability of being health aware is going to be the sum for all these 4 first entries here in our empirical distribution. So we're going to have 2/16 plus 0/16 plus 9/16 plus 1/16 is going to be 12/16. And if we divide these 2 numbers, we have 1/6. That is our estimate for this parameter here, right? So it is good to compute this empirical distribution in order to see that what we do to compute the parameters is basically a process of estimating the empirical distribution, eliminate the variables, and come out with the results. Just to emphasize that, I haven't already said that before, but it's important to think that in order to make things more efficient, what we usually do is go directly from this ratio here to this answer here. So what we do, we are interested in the probability of S and age. We go directly to the data and we count the number of cases that we have. So we're going to come out with the number 2. And we go directly to the data and we count the number of cases that we have a health aware person. So we're gonna go directly and we come out with a number 12. And from this ratio here, we compute 1/6. So it's more common and more efficient in terms of processing and memory to go directly from the data to the frequencies. So we can put together these two things, the empirical probability and the Bayes conditioning, in a single variable. So we can estimate a parameter that is theta x given u by using this notation here. So this is going to be the definition. We're going to use this ML here on the top, and I'm going to explain that later, but this is the maximum likelihood. I'm going to say that the parameter estimated in this form corresponds to the maximum likelihood estimate for this parameter. So I'm going to be the empirical probability for x given u. So x is a variable, u is a set of parents, and basically it is a ratio of the count of x and u by the count of u. So in the case of the example that we had in the previous slide, that we were interested in computing the theta of s given age, right, that was this parameter here, that was 1/6, we can count it directly. We had two cases that were matching the s and age, and we had a total of 12 cases matching the age, that is the parent, right? So we have 9, 10, 11, 12. Then it's going to be 1/6. That is exactly this number that we have here. And we can do that for all the parameters. For instance, we have age here. So what we can do? We have age equal true. These instantiations here are going to be 12/16. We have age equal false, and then going to be 4/16. So this guy here is 3/4, and this guy here is going to be 1/4. And we can do that for all the parameters that we have. So something that is very interesting about those parameters is the fact that they are functions of the data set that we have. So what I mean is that if we are computing these theta parameters, let's just think about one of them. I will call just theta. If we are computing this parameter theta, and we have several data sets that we don't have, but we can imagine the situation where we have several of those data sets, and we compute theta for the different data sets, the thetas will be slightly different because the data sets are slightly different. So we can expect that if we compute theta, we're going to find the theta over here, and for another data set, it's going to be like here, for another it can be like here, for the other one like here and there, and so on. And will be close to each other, we hope at least, and they will be not exactly the same value. They will have certain variance because we have different data sets. And there is one interesting property that comes from the central limit theorem that says that this parameter theta, they will have an approximated normal distribution. And that is very interesting. It's like, say, we can put a distribution over here, and that will have this shape where the average here is going to be P of x given u. So it means that the way that we are computing the parameters using the frequencies is basically an unbiased estimator for the true parameter. That is very good. And also we will have this variance here. So because it's a normal distribution, we can compute bounds that are tighter than the bounds that we computed in the previous lecture. When we discussed the Hoefflin and also the Chebyshev bounds, those bounds were for any distribution. They are valid for any distribution. Doesn't matter what distribution we're talking about. Now we are talking about one specific distribution that is a normal distribution. So we can compute the variance that is this equation here. We can transform the variance into a standard deviation by computing the square root and use the square root to compute a confidence interval. So we can put a confidence interval here, and because we have a normal distribution, we can show that if you are interested in 95% confidence, that's going to be 1.96, the standard deviation, so minus, and plus 1.96, the standard deviation, that is the square root of the variance that we have here. And this confidence interval is very important because it's telling us that with 95% probability that the true value of this parameter is inside this interval here around our estimate. So we want this confidence interval to be as small as possible. So we're going to be as tight as possible because we're going to be very confident that our estimate is very close to the true value of the parameter. So basically what I'm saying is that we want this variance to be as small as possible. We like estimates with a small variance because there is very small chance that the true value of the parameter is far away from our estimate. And in order to reduce this variance, what we have to do, we have to analyze that. We see that this variance depends on three quantities. One is the probability of x given u, another one is n, and another one is p of u. And to reduce the variance, we can, for instance, increase the denominator. So if the denominator is very large, you're going to divide by a large number, we have a small variance. But we have two competing factors here. We have n, that is the size of the sample, and we have p of u. So it's very clear that if we increase n, we decrease the variance. So the more data we have, more confident we are about our estimates. But we have this competing factor p of u here, saying that if we have a very small p of u, we're going to have to increase even more the sample size to compensate the small p of u. So in summary, we need to be very careful in the case that we have these small values, small probabilities for a certain instantiation of the parent for the parameter that we are computing, because if we have this small probability of u and we don't have a very large data set, we may end up with zero counts. And zero counts is a problem because you're going to have undefined probabilities, right? So we should try to avoid this as much as possible. And we should also try to avoid as much as possible to assign zero to those probabilities, because if we do that, we may have problems in the inference, because we're going to multiply zero by other probabilities, end up with zero probabilities that may not be a correct way of dealing with those estimates. So we haven't seen before. One possibility to solve this is to have the Laplace smoothing. Another possibility is to use Bayesian learning. That is a topic of a lecture that we will not cover in this course, unfortunately, because of time. But it's interesting to know that Bayesian learning provides several different results, but one of them is the fact that it presents a sort of a statistical justification for Laplace smoothing. But we know Laplace smoothing, and we can use that technique to solve this problem. All right, I think that is good for this first video. We're going to continue in the next one. We're going to discuss the maximum likelihood estimates. See you soon.